In this topic, we'll look more broadly at the design of instruction set architectures, using the particulars we learned about the ARM ISA as a starting point. One of the biggest principles of ISA design is that bits are precious. We saw how carefully the ARM architecture uses bits, and this is typical of ISAs in general. The main reason for this is that larger instructions are more expensive. We could, for instance, gain a lot of bits to play with by increasing the ARM instruction size from 32 to 64 bits. Clearly, this would make programs take twice as much memory, but the bigger problem is that loading the instruction takes time, and will take more time with longer instructions. It's easy to overlook instruction loading time as a cost, but instructions are data just like anything else, and the CPU must load each one from memory to run it. Big instructions slow down the processor. So, we make the most of the bits we have. And question 1. Cite at least 2 examples from the prior topic on ARM ISA design that show clever optimization of bit usage. Here's a copy of the instruction format chart for reference. The answer here is that a number of examples are really possible. For instance, the clever use of fixed bits of varying length, or the design of operand 2 constants in data processing instructions, or the implied addition of a 0, 0 to branch offsets, and also the implied 1 point at the start of floating point mantisses, and so on. Question 2. Cite at least 2 examples where bit field constraints present a significant limit in the ARM ISA. The answer is there are a lot of possibilities here, really, including, for instance, the range limits on LDR and SDR offsets, LDR and store offsets, I should say, or limits on operand 2 constants in data processing instructions, or an inability to use a constant in a mul instruction, and so on. All right, question 3. One way to cut down on LDR-SDR memory accesses, which are very slow compared to register accesses, would be to have more than 16 registers, so we can hold more data in registers. The hardware cost of doing this is negligible. Registers take up very little of the CPU circuitry, and we could easily have many more. So why not have a choice of, say, 64 registers instead of just 16? Consider the impact on the format of the instructions. The answer here is that the register fields in the assembly instructions would need to be 6 bits long to count from 0 to 63, and that would add 2 to 6 bits to most instructions. In the ARM design, we saw a pattern of different length fixed bit prefixes on instruction types, e.g. 00 for data processing, 01 for load and store, 100 for load multiple, store multiple, and 11 for branch. This pattern has an underlying theory and a formal name: prefix codes. Prefix codes often show up in ISA design and in many other contexts as well, including data transmission and compression. A prefix code is a set of bit patterns of varying length designed so that no pattern is a prefix of any other. Perhaps they should have been called non-prefix codes. Here's an example. No code in that set is a prefix of any other. For instance, the existence of 00 as one of the codes precludes other codes that start with 00. Ditto for 01. And the 100 code precludes other codes with a 100 prefix, as does the 101 code for its prefix. Question 4. Think about adding more codes to that set, following the rule. Can you add a 2-bit code? Can you add more than one 3-bit code? The answer here is you can't add any 2-bit code. All 2-bit prefix patterns are already in use. So a new 2-bit code would violate the no prefix rule. You could add a 3-bit code, 111, but you can't add two 3-bit codes, since any other 3-bit code would either be a prefix of another code or have another code as its prefix. Question 5. It is nonetheless possible to add more than one new code if you go to longer lengths. Can you add two more 4-bit codes following the rules? How about 4 more 5-bit codes instead? Now, the answer is 2 4-bit codes would be 1110 and 1111. And 5-bit codes instead could be 1100, 1100, 11101, 11110, and 11111. A helpful way to look at prefix codes is to consider them as the first part of a longer word. Let's use a 4-bit word as an example, with all patterns shown here. Each prefix code you choose effectively uses up all bit patterns starting with that prefix. A code of 0, for instance, uses up half of all patterns, since it precludes any other codes starting with 0. A 2-bit code like 10 uses up a quarter of the available patterns, all those starting with 10. And a 3-bit code, say 110, uses up 1/8 of the patterns. It's common for ISAs to distinguish machine instruction formats by putting fixed bits at the start of each format, but the fixed bits must generally be a prefix code. Otherwise, if, say, instruction format A has fixed bits 10 and B has fixed bits 101, both shown here in the diagram in red, violating the non-prefix rule, then any A format instruction whose first non-fixed bit is a 1 will look like a B format instruction, since it starts with 101. Format B must use a 3-bit fixed pattern that starts with something other than 10 to be distinguished from format A. To design a prefix code, you decide how many short codes versus how many long codes you want, budgeting how you allocate the prefix space, if you will. If you're designing the fixed bit parts of an instruction set architecture, you give shorter prefix codes to instructions that need more free bits to work with, and thus have fewer fixed bits. But the trade-off is that other instructions must suffer with longer fixed bit prefix codes and fewer free bits. You can tell which instructions are more important by the number of non-fixed bits given them. For instance, the LDR-STR instruction's prefix is just 2 bits long. The ARM designers could have made that 3 bits to permit shorter prefixes for other instructions, but that would have left 1 fewer free bit for the LDR-STR, which would probably have come out of the offset field, and that would reduce the range of address relative offsets from 4095 to 2047. LDR-STR are so common and important that it was worth giving them just 2 fixed bits. Almost all the ARM instructions we've been learning have short fixed bits prefixes because they are the most important in the ARM ISA. Note, by the way, that the multiply, multiply long, and swap instruction formats in the ARM ISA violate the prefix code rule by having fixed bit patterns that start with 00. But they have an additional 4-bit fixed pattern in bits 4 through 7 to distinguish them from the data processing format, which forbids 1001 in those bits unless it also has a 1 in the S position. Question 6. Design a prefix code for a 32-bit instruction set architecture like ARM, but without condition codes. There are 3 instruction formats, each with different numbers of free or non-fixed bits. One with 31 free bits, one with 30 free bits, and another with 29 free bits, respectively. design a fixed bit prefix code for those three formats. Don't worry about the free bits. This is just about the fixed bits. If a fourth instruction type is needed, how many free bits can it have at most? The answer is we'll need fixed bit prefixes like 0, 10, 110. Such a prefix code uses up 1/2 plus 1/4 plus 1/8, 7/8 of the available bit patterns. This limits the fourth format to a 3-bit code, for instance 1111, and just 29 non-fixed bits. Prefix codes are used in other areas than ISADesign, most importantly in data compression, where it's common to set up prefix codes to represent, for instance, the letters of the alphabet, with shorter codes for common letters and longer codes for uncommon letters. Since the shorter codes are used more frequently than the longer ones, the total data needed is reduced.